Welcome to week 3. Now in this week, first we will do a quick recap on the things that we have done so far, and after that we can move into improper integrals. Right, so to start with, let's see what are the techniques that we have done in integration. So now the first technique kind of a technique is to see whether we can simplify the integrals. That is, for example, if we consider things like this, you can see now in the first example we have the square root of x multiplied with 1 plus square root of x. So now if we try to do the integral by considering the inside function as a product of two terms, if we try to target this one as a one unit, then it will be difficult. Okay, sometimes the integration by parts will work, but I don't guarantee that one. Okay, I don't think the integration by parts even will work in this case, right? So anyway, it will be a very simple situation if we just solve these two brackets, right? I mean, if you multiply this square root of x throughout the bracket, you will obtain two very simple functions with an addition in between. So we can just write down the integral like this. Okay, we know the answer from the standard results. And how about this one? See, just if we consider this as a division, then it will be like we will not have any clue on how to simplify on how to find the integral. But if we just write down the corresponding sine and cosine values for all these trigonometric functions and then simplify it, you can see everything will reduce down to the integral of sine 2 theta, where we know the answer from standard results, right? Now, especially if you have all this tan and secant and everything mixed up, it's a good practice to convert all those trigonometric functions into sine and cosine theta. Okay, so it's not a theorem kind of a thing, it's not an exact rule, but most of the times it will work. If you have lot of trigonometric terms within the integral, first try to see whether you can convert all those stuffs back into sine and cosine theta. Okay, so for that we will need the corresponding relationships for tan and secant and cosecant. Okay, so tan will be sine theta over cos theta, secant will be 1 over cos theta, and cosecant will be 1 over sine theta, and also cot theta is 1 over tan theta. That means the reciprocal of this one. Okay, and see, now even for this one you have a product, right? This term squared, and if you just if you directly compute the square first, you will have simple terms across addition, right? So you can just get the integral separately on each of these three terms. Now for this one, once again we can use this relationship, right? Where sine 2x cos 2x is equal to sine 2x. This is the double angle formula for sine. This is just a one simple thing that you should try before integrating. Okay, all the time this will not work, right? But it's not a universal rule kind of a thing, but it's a good practice to see whether you can do some simplifications before dealing with the integral. And the second point will be to see whether you have any obvious substitutions. for example, an integral like this, we can see if we substitute u equals x squared, we will obtain the relationship between du and dx like this, right? Du is equal to 2x dx, and here we have that x dx term. See, so it's just a matter of combining it with a number, which can be done very easily, right? So, like now, as I said before, these are not universal rules, right? But you should check these whether these factors are there, whether these properties are there before going into those complicated calculations. Okay, so first see whether you have any obvious substitutions where you can manipulate easily, right? So failing all those two things, then we can check, we can make use of the information or make use of the theory that we learned throughout these 2 weeks. Okay, and they will be right. So throughout these 2 weeks we covered these sections, right? So if we have our integral with trigonometric functions, and if we have it like something like this, what we can do is we can use the techniques that we did in the section 7.2. Remember, we check whether these powers are odd or even, and then apply the results accordingly, right? And if it is a rational function, and be careful, what I mean by rational function is something with the numerator and denominator, but in both numerator and denominator you need to have polynomials. Okay, say for instance, if you have a numerator with a trigonometric function and a polynomial in the denominator, you won't be able to use the partial fraction techniques, right? So the partial fraction technique that we did in 7.4 is valid only when you have polynomials in both numerator and denominator. What is a polynomial? It is a finite number of terms with some degree with 4x, right? Something of this nature, right? This goes up to a1x plus a0, right? So here we have finite number of terms, and in each and every term you have a coefficient for x. It can either be 1 or some number, a negative number or a positive number, or it can even be 0, right? Also you have a certain degree for x, right? This degree can also be 0 or 1 or 2 or some sort of an integer, right? And this cannot be a negative value, right? If it is a negative value, then the x term will be something like this, and we don't consider these stuffs as polynomials, right? Okay, but anyway, if we have things like let's say this one, we can still convert it to a polynomial, rational function of 2 polynomials. Okay, if you just multiply it with the corresponding common denominator, you will get x plus 1 over x to the power of 5, right? So this becomes a polynomial. And for integration by parts, what we look for is a transcendental function. That means if we have ex or sin x, cosine x terms along with a polynomial, right, then most of the times the integration by parts technique will work. Okay, and also the thing that you should consider when doing integration by parts is when you differentiate, the complexity of a certain function will be reduced, right? But now if we consider these two things, no matter how many times we differentiate, ex will stay the same, and it is also true for sin x, because sin x will be changed to cosine x upon differentiation, but the complexity, like in the sense it is not reduced down to a simpler version. But say if we differentiate a polynomial, then the terms will be reduced eventually. Okay, so we should be careful when selecting the appropriate function to differentiate and to select as u and dv's. Okay, and then finally we come to radicals, right? So radicals means the form of this one, right? So this can either be plus or minus, and also this one, and accordingly we discussed certain types of, like, remember there were 3 categories of substitutions. For example, we have a thing called a sine theta, right? And also we have a special range for those theta values, right? So this is basically everything that we done so far. And also I should say, now sometimes even to apply one of these categories we need to do some manipulations. Okay, say for example, if we have an integral of 1 over 1 minus cos x dx, before considering any of those techniques that I mentioned before, we can multiply this one with its conjugate, right? That means we multiply 1 minus cos x by 1 plus cos x, and like multiply and divide, right? So then now these techniques are not mentioned in the ones I wrote down before. Okay, so these kinds of manipulations will come with practice, so that's why you need to do lot of problems, at least like simple problems. When it comes to integration, you need lot of practice, right? So in this case, when you multiply and divide by its conjugate, the problem will reduce down to cos x squared x plus cos x over sine squared x, right? Thereafter you can use those techniques that we described before. And finally I want to say that now these 4 methods might not, like, it doesn't guarantee that we can use one out of these 4 methods to solve any integral, right? Now I am not going to describe this in detail, but for integrals like this, e to the power x squared dx, we cannot use any of those techniques to find the answer for this one. Okay, but we can of course find the answer for this one, right, by a substitution for x squared. But no matter how hard we try to integrate this function, we will not be able to do it with the techniques that we have learned, right? So we need some more additional knowledge, but we are not going to discuss it within the scope of this subject. But anyway, I can assure you that for all the integrals that you get within this subject, you have a direct answer, right? So make sure that you practice all these techniques by doing lot of problems.